Hey, welcome to the first lecture of topology. In this lecture, we're going to introduce topology. So first of all, let me offer a definition. So a topology T on a site X is a collection of subsites of X such that, first of all, the empty set and the whole space lives in T. Second of all, for U and V live in T, we have U intersects V also lives in T. And thirdly, for a collection U alpha, where alpha is indexed by I, where I is an arbitrary index site, countable or not, lives in T, we have the union of alpha in I, U alpha, also in T. And I want to stress that this definition of topology is defined by open sites. So that is equivalent to say, if we are using open sites to define a topology, then the finite intersection of open sites is still open, and the arbitrary unions of open sites is still open. And in some other literature, we may see another definition for topology, using instead the closed sites. So if we use closed sites to define a topology, we remain everything unchanged except the last two conditions. So we make the first condition unchanged, and the second condition becomes for U and V lives in T, their closed sites, we have U union V also in T. That is, a finite union of closed sites is still closed. And thirdly, if U alpha is a collection of closed sites in T, we have the arbitrary intersection also lives in T. And in our lecture, we're going to apply the first terminology. Before we proceed, let's just observe what a topology is. So, given a set X, same as the definition, we induce a structure for topology. So, we may say a topological structure. And since we are studying topology, there must be some so-called topological properties. And if you are familiar with the abstract algebra, we know that in studying the algebraic structures, or the algebra, we also have a structure which is still generated by a site called algebraic structure. And we also have the algebraic properties. And recall that in algebra, if a morphism or if a function I from X to Y preserves the algebraic structure, then we call I an isomorphism. So in studying topology, we also concern such a morphism or such a mapping. But in topology, if a mapping or morphism preserve topological structures between two topological spaces, we instead call it a homeomorphism. In studying topologies, we need some methods we are already familiar with. Comes from the metric space. So first, let us recall what a metric means. So a metric is a function d on a site x. It is a function from the Cartesian product of x and itself to 0 and infinity. It satisfies three conditions. First of all, d of xy equals to d of yx. And second of all, d of xy is always greater equals than 0. This is directly derived by its range. Moreover, d of xy equals to 0 if and only if x coincides with y. And thirdly, we have the triangle inequality. That is, for dxz, we have it is boundable by distance between x and y plus distance between y and z. And this holds for all x, y, and z in X. And also we say a metric space. So a metric space is a set X equipped with a metric, namely D on X. So one very familiar metric space is the Euclidean space. Euclidean. So the Euclidean metric defined by dxy is equal to I from 1 to n of xi minus yi squared, all square root on Rn is a metric called Euclidean metric, and this Rn and such a D is a metric space. So even we are using some results from metric space, but we still need to stress one thing, that not all, or let me state it another way, that is, topological properties, they may not equal to metric space properties. For example, the completeness is a metric space property instead of a topological property. So yes, we are studying topology since it is a collection of sides, of subsets of a given set X. So we concern the open sides and closed sides in a topology, since we are using these two concepts to define a topology. First of all, let us recall what open means in metric space. Before that, we introduce a concept called open ball. So let xd be a metric space. So for x lives inside X, an arbitrary point, and an r greater than 0 arbitrary constant. We say an open ball B R of x. So BR of x in some literature, one may say it is BXR or BRX, but they all mean the open ball. And in our lecture, we're going to apply this terminology. So this means an open ball centered at x with radius r and it is defined by B R of x is defined, of course, by a metric. So all y in x such that d of xy is less than r. And since it is symmetric, this is equivalent to this. And if we are going to define closed balls, we just make the inequality. We just assign equal sign to the straight unequal sign. Okay, so a lemma. This is a very useful lemma. So still, XD means a metric space, and X is a point in X. R is greater than 0, a constant, and BR of X is an open ball defined as above. Then, for all Y lives in the open ball BR of X, there exists a row greater than 0, such that B row of Y is a subset of BR of X. The proof is quite simple. So, since Y lives in BR of X, then by definition, we have R greater than d of xy. So that means R minus d of xy is greater than 0. So we may choose our row to be this. So let's row defined by R minus d of xy. Choose a point Z lives in B row of Y. So Z lives in B row of Y means, by its definition, that d of y to z is smaller than rho. And that means d of yz is smaller than r minus d of xy. So let me just use an equal sign here. Since rho is defined to be this guy. So that means r is greater than d of yz plus d of xy. And this guy, by triangle inequality, it is greater or equals than d of xz. So r is greater than d of xz. This means our x lives in our z lives in BR of x. And since our z is arbitrarily chosen, that means for all z lives in B row of y, z also lives in BR of x. So that means B row of y is a subset of BR of x. So we're done. Now we introduce the power sides, or we recall the definition of power sides. So given a set x, the power side of x, let us denote it by p of x, where p is script p. It is the collection of all subsets of x, including the empty set and the whole space itself. So it is defined to be all, namely A, such that A lives in set x. So remark one thing. For all topology T on X, we always have T is smaller than P of X. Note that in saying this statement, we mean two things. First of all, P of x is a topology. And second of all, they are T and P of x. They are comparable. Note that not all topologies are comparable with one and another. And moreover, since we are applying the definition of topology induced by open size, so we may call all the elements in a topology T open set. So now we can define the open side or more precisely, let us recall the open side in a metric space. So still, and this definition is induced by the open balls and also this lemma. So XD is still a metric space. We say a subset U in X is open if for all X in U there exists an R greater than 0 such that dr of X is content in U. And similarly, we can define the closed sets. The closed sets in a in metric space, we say A lives in X is closed if X minus A is open. Note that even though we're defining open size and closed size in such a way that they are by taking the complements. So they are like one is the complement of the other. But note that we are in metric space. But in topological space, there are sides that are mutually open and closed. This is very anti-intuitive. Before we introduce that, let us recall the last terminology called neighborhood. So a neighborhood U lives in X. So a subset U in X is called a topology. It's called a neighborhood. Sorry, my bad. Of X in X, if there is an open set V such that X lives in V containing U. And recall what we left off. The power size is a topology. And indeed, so let me give the example of topology. The first topology is the indiscrete topology. So if we let X be a set, the indiscrete topology we may define denoted as T min on X is defined to be only empty set and a whole space. And the discrete topology, namely T max, is the power side of X. Remark. So they're named by this way for a reason. So for any topology T on X, we have T min is smaller than T. And for any T on X, we have T is smaller than T max. And thirdly, for all X in X, the singleton also lives in Tmax. So still three things. One may convince himself that Tmax, the power set, is indeed a topology. We will not prove this in our lecture. And second of all, still, the comparability we have not introduced yet. Like the criterion for being comparable between two given topologies. We will introduce that later. And the third property, the third remark, is very important. Since all the singletons lives in Tmax, so that is all singletons in discrete topology, they are mutually closed and open. Moreover, all the mappings from discrete topology are continuous. So we first introduce some notation for being comparable. But note that this is not the criterion for being comparable. So we say that T and T prime are topologies on X if T prime is bigger than T. We say T prime is finer or larger or stronger than T. And if T prime strictly contains T, we say that T prime is strictly finer, strictly larger, or strictly stronger than T. And if T prime is smaller than T, we say that T prime is smaller or coarser or weaker than T. And similarly, if T prime is strictly smaller than T, we say that T prime is strictly smaller or strictly coarser or strictly weaker than T. And we say that T and T prime are comparable if either T prime bigger than T or T prime smaller than T. Or maybe we all use smaller sign. And recall that our metric space, the relation of a metric space and topological space, why metric space is so often mentioned in the study of topology. One of the reason is that a metric space is automatically equipped with a topology. For example, we just mentioned the Euclidean. So all the metric space is automatically equipped with a topology. But there are some topologies that come from there is a topology that comes from different metrics. So that is an example. So if we consider x equals to R2, and our d infinity is the metric from R2 to times R2 to 0 infinity, be such that the infinity of xy is defined to be the maximum of absolute value xy minus y1 and x2 minus y2. So one may convince himself that d infinity is indeed a metric. And second, our open balls with respect to our d infinity are open squares. And thirdly, one can prove that the open sides defined in this way are exactly the same as the open sides defined by Euclidean metric. So therefore, their topology derived from either the infinity metric or the Euclidean metric is the same. That is T induced by the infinity and T, the Euclidean, they are the same. But they are different metric. So yes, there is a topology that generated by defined by different metrics. And also, not all the topology are derived from a metric. There are some topologies that come from no metric. So, example. So, if we consider the topology defined by open sides, union, all U lives in R, such that R minus U is finite. So we claim first that T is a topology. So since empty set lives in T by definition, and R minus infinity by this definition also in T. So the whole space is also in T. And second of all, for U and T and V in T open, so without loss of generality, we may assume that they are all non-empty. Otherwise, we can use the first property to derive the result. So they are all non-empty and R minus U, R minus V by definition are finite. And our goal is to show that R minus U intersects V is also finite. So R minus U intersects V equals to R minus U union R minus V. And obviously, this is a finite union of finite sets, which is finite. Therefore, U intersects V also lives in T. And it left us to prove the arbitrary union. So let U alpha, alpha indexed by I, be open sides in T. And still, without loss of generality, we may assume each of U alpha is now empty. Then we have R minus union of all these U alpha is the intersection of all R minus U alpha. And since the finite intersection of finite side is also finite, we're done. Therefore, T is a topology. And indeed, T comes from no metric on R. And also, before we end our lecture, we shall introduce something that we shall concern in the study of topology. So first of all, we need to characterize the objects of topological spaces, the construction and properties. So objects are open sides, since we are defining the topology by open sides. Now our construction. In fact, we haven't encountered any construction yet, except perhaps example 3. For properties, let me regard the definition of topology by OpenScience, a property, and in some literature they are called the axioms of topology. And of course, we shall be interested in the relations between objects. So, for example, the comparability. And also, we are concerning the operations. Not only the operations between objects, but also the operations from different topological spaces. And back to our starting point. Yes, for some mappings that preserve that for a mapping between two topological spaces that preserve the topological structures, such a mapping is isomorphism since it preserves the structure, but in topology, we call them homeomorphism. We will encounter them later. And perhaps we shall concern the generating basis. In some applications, for if we concern a very big space, a very big topological space, it may not be very efficient or economic to analyze all these objects. And there are some smaller sites that contain the enough information of the whole space. And this is the basis. And yes, topology has basis, and basis generates topology. And also, since we talked about the relations between objects, but we introduced the relations or transformations within spaces. But in fact, we should make it in another category. Sorry, it's within spaces. Sorry for the typo. And 6, we may concern some like key features or some underlying properties. But anyway, this might be too loosely speaking, but I think this perhaps offers some insights for our studying in topology. Okay, so that's all for the first lecture, and in the next lecture, we shall introduce the basis for topology. Thank you for watching.